There's four main topics that we need to cover. There's the definitions and laws of thermodynamics. There's the heat equation. There's the gas laws. And then there's some work energy equations. I really need to change up this whole unit. But this year I've been extremely lazy. I changed the order, but now I'm regretting it. Because I wanted to go over heat equation and gas law because those are the two main important things, along with this table of equations. So, how's your Greek? I don't understand why y'all don't learn Latin and Greek and English. It makes no sense. They really need to change their English class because it's very important. What percentage? What is the English language made of? So English language composition. Let me actually look that up. Well, that's irrelevant. See if I can find. What's the composition of English language? That's a good picture of it. So, English language. Green is Germanic. Green is English. So English comes from Anglo-Saxon language, which was Germanic. So this portion right here is the core English. That's your the, and, a, has, have. That's your 3 or 4 letter words used in English. Next we have French. So French words. Then we have Latin. Latin is bigger than the main core English. Then we have Greek right here. Other language influences, and what's that yellow? Yellow is not close. Well, Latin, French. I mean, technically, you can argue most of the French though is from Latin. Derived from proper names was the yellow. So French is Anglo-French too. So Germanic and French would take up the core aspect. Any Anglo-Saxon and Germanic languages. So Germanic would be Old English and Middle English, Old Norse and Dutch, Anglo-French. So a large portion of the language comes from Latin and Greek. So let's look. Let's review some of our. Let's start with the easy one. Isothermal. What does this word mean? What does ISO mean? What does the word iso? What does the prefix iso mean? What do you think isothermal is? What's another word that has the word iso in it? Alright, name another one. isosceles triangle. Word iso means equal or same. Thermal means temperature. So if something is isothermal, it has the same temperature. Or in other words, constant temperature. Meaning you're keeping the same temperature throughout. It can either be used to refer that temperature doesn't change with time, it stays the same. Or it can mean that two objects have the same temperature. What about isobaric? What does that one mean? What is something that uses the word barbaric? Ever heard of barometer? So you have heard of it. So the device meant to measure pressure. So constant pressure. Meaning you have the same pressure throughout the process. Then lastly we have, well not lastly, there's two more. Then we have isochoric. I will admit that this one probably have no clue, but we'll take a guess. Because choric is very hardly ever used. Trying to look up the etymology. Comes from like chorus. Belonging to, spoken by, resembling a chorus in a drama. How do you derive isochoric then? It means constant volume. Not sure how this one gets its name. Entomology. That's because I was looking up the Latin word. The Latin word choric is from chorus. But this is Greek. This comes from the Greek word which if you Latinize it, it's meaning space. And this is supposed to be a row. Then last word we have is adiabatic. What do you think adiabatic means? So what does the Greek prefix a mean? Atypical. What does atypical mean? What does atypical mean? Okay, what does typical mean? Something typically happens. What does that mean? Alright, and what happens when you put a in front of the typical? If something is atypical. So a means not. It's a negation. Dia means through. The ick is English. And this means batic. Comes from batos, meaning passable. So basically it means impassable. What this means is no heat in the context of thermodynamics. No heat is removed or added. And my chi is horribly drawn. Looks like an X. I don't know how you do a chi. It's supposed to be like super narrow on the bottom. But you don't need to know Greek letters, or Greek words, the origin at least. Just that they're variables, not the actual language. But anyway, so in thermodynamics, we have this idea of doing work. So recall that work is the change in kinetic energy. Work is force times distance. And we have this concept. So let's suppose we have a system. So in our system, we have a closed system. This would be everything of importance. Everything we deem important. Everything we are analyzing. And then we have surroundings. And this is everything other than our system. So here we have some system that we closed off, and then we have surroundings outside. So we can do two things. We can pump heat into our system. So I'll let it be Q, which will represent heat added to the system. And our system can do some work. So work done by the system. We can thus analyze our system and surroundings with the following equation. The change in internal energy, and that's supposed to be U, is equal to the heat added to the system minus the work done by the system. So this will be change in internal energy. This will be heat added to the system. And this will be work done by the system. You can think of Q as the energy we are inputting or adding to the system. And work is energy that is used up when doing useful work. So think of a car engine. So in order for a car engine to work, we need to give it some energy to work with. So that'd be adding more gasoline to the system. There's a lot of chemical energy stored in the chemical bonds of gasoline. So in order for a gas engine to work, we're going to have to add some energy to it. As it uses this energy, it's going to start causing the pistons to turn and move, and this is going to be energy lost or consumed. So energy that is used up or consumed when doing work. And most of the time, this is going to be lost due to heat. So this work is equated to some heat loss. Um, but the amount of heat that is lost is equivalent to the work done. So let's analyze an isochoric process. So isochoric means the change in volume is equal to zero. Our volume stays constant. How much work is done during an isochoric process? What would be the equation for work for an isochoric process? So let's imagine a piston. Let's look. Do you know how your car works? So we have a piston in here, and we have some gas here. What happens if this volume of gas doesn't change? What does the piston do? What'd you say? Yeah, it'll start to keep the same volume. So what does the piston do? Nothing. So how much work is the piston doing? None. So work is equal to 0 joules. Now isochoric system. If the volume doesn't change, then the piston is doing no work. So the equation for heat. So I should illustrate that there's going to be three major things we're going to be looking at. We're going to be looking at pressure, temperature, and volume. So the equation for energy, heat energy added. So basically what we're going to be doing is adding temperature and temperatures of the system, or heat energy to the system, and this is, but we're going to change the pressure such that the volume stays constant. This is going to be your mass times Cp times delta T, but that's not it. We'll have a slightly different one. It's N times Cv times delta T. So what this is your heat energy, how much heat you're adding to the gas. This is your number of moles. And this is your molar heat capacity for constant volume. And then we have our change in temperature. When we were doing the heat equation, and we've been using slightly different versions of this, we've been dealing with just heat capacity and not molar heat capacity. So do you know what a mole is? So do you know what a dozen is? So you have 1 dozen eggs. That's equal to 12 eggs. If you have 1 mole of eggs, you have 6.022 times 10 to the 23 eggs. So, an insanely big number. Basically, this is more used in chemistry. When we're dealing with gases, and especially when dealing with gases, we're basically we can't worry about mass too much when we're dealing with gas, and so we have to actually count how many particles there are. In 1 glass of water, you probably have a couple moles of water molecules. So there are an insanely high amount of atoms and molecules in a substance. So this is a counting number. And you can write the CP values. You can write CP or CV in terms of either grams or moles. For a gas, it's more useful to look at it in moles and instead of grams. There's a nice conversion, but for the purpose of this class, I'm not going to go into it. If you're curious of how to convert between moles and grams, you pull out your fancy periodic table. If you ever looked at a periodic table, let's figure out the ratio of moles to grams for water. So the chemical formula for water is H2O. Hydrogen has a molecular weight of this. So we have 2 hydrogen atoms. So we do 2 times 1.00794. Then we have 1 oxygen. Looking it up, oxygen is this. So it'd be 1 times 15.9994. We add up those 2 numbers. So 2 times 1.00794 plus 15.994. And we get that water is 1 mole of water is equal to 18.01528 grams. These numbers on a periodic table is how many, if you had 1 mole of sodium, you have this many grams. If you have 1 mole of iron, that's how many grams of iron you have. So it's a ratio. For every 1 mole of water, you have this many grams of it. So common gases would be like oxygen. There's 2 oxygen molecules, so you double that number. So it's about 13 grams per mole. And these are ratios. You can either write it as 1 mole per 18 grams, H2O, or you could write 18 grams per 1 mole of water. And this is just a conversion factor. Like if I told you it's $1 per apple, and I told you you have 7 apples, then that's $7. So we're going to get into the gas laws a little bit. So again, you can either look up this, and so this equation here, if you don't want to deal with moles instead of grams, you can rearrange it as Q equals mass CV delta T. But the value of CV has to be in per gram, whereas right here is in per mole. So it's just a constant, you look it up. And then we get, so our isochoric system, we have this relationship here. As pressure, or as temperature increases, what does pressure do? So imagine that we have this sealed container, the piston's stuck, and we're heating it up. What's going to happen to the gas inside? As the temperature of the gas increases, the pressure is going to increase. In particular, we get this equation. Pressure divided by temperature is equal to some constant. And note, this temperature is by itself. So what unit do we use? Nope. Kelvin. So must be in Kelvin. Nicole, you mind running to the printer? So if we have the initial pressure and divide it by the initial temperature, that must equal the final pressure divided by the final temperature. So initial pressure divided by initial temperature has to equal final. As temperature increases, pressure increases. This law is known as Gay-Lussac's law. Let me look up how you spell his name. And let's now look at isobaric. Nah, not yet. I don't want him looking at the answers before I tell him. Alright, so isobaric means the change in pressure is 0. So what do you think the equation of work is going to be? So let's think about piston. Alright, so we have, so remember, work is equal to force times distance, right? What is pressure? But you should know what it is. What is pressure? What is pressure a measure of? So imagine we have a sheet of paper. Pressure is caused by the force of little tiny molecules coming down and striking the paper and then bouncing off. Pressure is equal to the force, all these particles hitting and bouncing off, divided by some area. So how much force per some unit area is pressure? So we want to find work, so we want to find area. So let's see. So we know that pressure is force divided by area. So that means that force is equal to pressure times area. All right. So we can plug this in. Work is equal to pressure times area times distance. And what is area times distance? What is area times distance? So let's imagine we have a square, and then we were to raise, or let me do it like this. So imagine we have some square bottom, and then how do we find it? We find it by length times width. That gives you the area. And now let's multiply it by some height. What do I now have? The volume. Area times distance is just volume. Now, pressure stays constant, right? That's what isobaric means. So the only thing changing in this is volume. So work is equal to pressure times the change in volume. Equivalently, using more appropriate gas laws, you can also write that work is equal to nR delta T, where R is some gas constant. Likewise, we know the equation for heat is equal to nCp delta T. Again, if your Cp value is in grams, then you can change N to mass. We've been using Cp because Cp is for constant pressure. That's not what Cp stands for, but you can think of it as constant pressure. Likewise, Cv is for constant volume. When we're using our equation, we're assuming that the atmosphere doesn't change. That's what was going on. If the volume was being kept and the pressure was constantly changing, we'd have to use another value. Going back to this equation after I left something off, what would delta U be? Well, delta U is Q minus work, but work was 0, so our delta U is just our Q. The change in energy for isochoric is just how much energy we put into the system. If we don't put any energy in, the change in energy is 0, but how much energy we put in is going to be the total change in energy. For this one, the change in U is Q minus W. And I'll explain this in a little bit. You could also simplify this Q minus W. So it would be this minus this. In a little bit, we'll see how Cp and Cv are related, but delta U is equal to mCv delta T. The reason for this is Cv can be approximated as 3/2R, where R is that constant. And this only applies to gases. And Cp can be approximated as 5/2R. Again, these equations only work for gases. And now let's look at what happens. So we're keeping pressure the same. What do you think happens as temperature changes? So as temperature increases, what do you think happens to volume? Yes. So think of a hot air balloon. So as temperature increases, volume will increase. And thus we have a similar situation. As temperature increases, volume increases. And we end up with volume over temperature is equal to some constant. So initial volume divided by initial temperature is equal to the final volume divided by final temperature. This is known as Charlie's Law. And no, it's not. It's equal to Charles's Law. Then we have isothermal. So the change in temperature is the same. So here's an important thing to know in an isothermal situation. What would isothermal mean in a piston system? There is no change in heat. Well, no, pressure can change. It means that there's no change in energy. So I'll just give you this. The work is going to be equal to the heat, and heat is going to be equal to work.